Okay, so we are going to continue our discussion of differential equations by talking about some analytical solutions to these guys. So we're really going to be talking today about first order equations. That's all we really need to be talking about for single variable calculus, maybe with the exception of a spring problem. But we're going to be dealing with separable equations. The separable differential equation makes it really easy to solve. These separable equations you're going to see a lot in physics. If you've taken physics, you would know this is kind of how you jump between acceleration, velocity, and position, finding your displacement by integrating along some distance. So yeah, today we're going to be talking about separable differential equations. This is probably my favorite solution because the other one is a little bit messy, the linear equations I don't like as much. But we'll cover this now. All right, so what is a separable differential equation? So separable differential equation is when we have our derivative, and that's equal to a function of x times a function of y. Okay, so this is kind of interesting because we're dealing with functions of x and functions of y, but the separability really comes into play, and this is actually kind of interesting how we're going to be dealing with solutions to these, because we're going to exploit how this, when we're writing a derivative in Leibniz notation, it is dy over dx. So this is actually one of the few times where we will be treating this as a fraction and applying our arithmetic as if it were a fraction, which we don't usually do in calculus. Okay, so let's talk about how to solve these in generality. Okay, so how to solve. So again, say dy by dx is equal to f of x times g of y. So what we're going to do to make it easy to solve this is we are going to manipulate this so that we get everything on one side. So we get all of the x things on one side and all of the y things on the other. So we separate the equation. So we have something that looks like f of x dx plus or equals g of y. That kind of looks like a not equal sign. So we get f of x dx equals g of y dy. Now we have these differentials here on their own, which is kind of weird. We don't usually see that, but this is, again, a differential equation. So we're dealing with these little differentials. But what does this look like? This looks like it'd be really nice if we were to put an integral sign there. And if we put an integral sign there, then that also takes away the dx and the dy once we integrate our functions. So what we do next is we integrate our functions. So we integrate f of x dx, and then we integrate g of y dy. And from that, we're going to get some f of x equals g of y, where, of course, f equals the integral of f, and g equals the integral of g. Okay, so again, pretty abstract, pretty interesting though. Let's try an example, hopefully that'll clear things up. So for this example, we want to look at dy dx is equal to 6x squared times 2y plus cosine y. All right, so what we're going to do is we're going to cross multiply. So we're going to take this and multiply it with that. We're going to take this and multiply it by that with that. So from there, we're going to get 2y plus cosine y dy. And I guess I could put another dy there, but it doesn't really matter because we're going to integrate the whole thing. Get 2y cosine y dy equals 6x squared dx. All right, now we're getting somewhere. So now we want to integrate both sides. And you can imagine sometimes you might have a more involved word problem where you're going to need to put bounds on integrals like this. So, of course, in kinematics and physics, you're going to need to do that. Here we're not. We're trying to find a general solution. So we're going to get the integral of 2y plus cosine y dy is equal to the integral of 6x squared dx. Now, this is an integral. Both of these are integrals that you should be able to do. You can apply the linearity of the integral operator to separate this by the sum rule. Of course, 6x squared is a simple monomial, actually. So what we get in the end is, once we integrate, apply the power rule, apply trig rule, we get y squared plus sine of y is equal to 2x cubed plus c. And the kicker here is that we can't really solve for this as a function of x. So we really get just a curve, a general curve, with different kind of intercepts, because this c, of course, can vary. Now you can imagine you might have an initial value problem where you have something like y of 0 equals x, then of course that constant there would be altered. All right, so there is our kind of intro to separable equations. As you can see, they're pretty easy to solve as long as you know how to integrate, and as long as you're comfortable using the Leibniz notation for these derivatives. So next video, we'll look at some applied separable equations, then we'll be looking at some population growth and linear equations, then some predator-prey models, then we will be off to the land of infinite sequences and series. All right, see you guys in the next one. Bye.